Alrighty, here we are again, another week. Welcome, welcome. As always, please unmute yourself and ask any questions you have or type them into the lecture text channel on Discord. I've got that open so I can see it. So we're going to continue here then with chapter 20. We finished through 20.4, where we described the generic attack of a nucleophile on a carbonyl compound. So we talked about how there could be an R group here or a hydrogen, and in general, if a nucleophile attacks here, I'll push these electrons up. If the nucleophile is especially strong, maybe it has a full negative, it's already pretty unstable, then this combo will already be relatively high in energy, so it won't take a lot of energy to get to the first intermediate and transition state. And then if there's any product source around, this oxygen would pick up a proton to produce a product. Right, so we've seen reactions where this occurs. That those reactions include the Grignard reaction. If the Grignard is present, it's strong enough to come in there and attack and push electrons up. If you have a hydride, like lithium aluminum hydride or sodium borohydride, the hydride can come in and deliver protons, so that would just create another hydrogen here. We haven't really talked about any situation where the nucleophile is very weak. We did a little bit last week generically. We said if you have a carbonyl and a weak nucleophile, maybe one that only has a partial negative, then they won't very well react together, because if the nucleophile were to attack and push these electrons up, you would get two formal charges forming at once. As if the nucleophile is not negatively charged in a formal sense, that means it's neutral formally. It would have a partial negative, but it would be formally neutral, and when it forms another bond, that would give it a formal positive. So you'd be forming a couple formal charges there, and that's pretty unstable. So we said to make that easier, you'd first add an acid, and the oxygen here would first pick up a proton from the acid, making it positive. Then, since there would already be a proton there making that positive, that would be significantly higher in energy. So it wouldn't have to reach such a high energy transition state for this attack to occur. And when the attack does occur and electrons swing up, this oxygen would already be protonated, so it wouldn't have a negative. And so that would be much more reasonable. Now the nucleophile would probably also have a proton which could be removed to bring electrons in and balance its charge. So there's a couple different ways this can go down. The main thing it depends on is the strength of the nucleophile. So that leads us to, that brief review leads us to the new content we're going to cover today, starting with a situation where water is our nucleophile. And we know water is generally a pretty weak nucleophile, right? The water molecule does not have anything more than a partial negative here to attack, and when it attacks, it'll form a formal positive on the oxygen. That's pretty unstable. So if we want water to attack a carbonyl, it's probably not going to work well, whether we have an aldehyde like this or a ketone where both are R groups. Either way, it's not going to work very well if the water just tries to come in here and attack. Because the water, even though it's got a nice partial negative, it's relatively stable, and the carbonyl is pretty stable overall. So if that attack were to occur, to create two formal charges at once, that would be much more unstable than the reactants, and we'd be looking at a situation where the reactants are so stable compared to the intermediate that the transition state energy we have to get through is quite high, and with such a high activation energy, this step would almost never occur. So it's a kinetic issue we have. We haven't really looked at whether the attack of the water makes sense from a thermodynamic perspective, but this first step doesn't work well from a kinetic perspective. So what we need to do, skip this bullet point, come back to it in a minute. What we need to do is to add an acid to improve the reaction. If we have an acid present and the carbonyl picks up a proton from the acid first, now we have a situation where not only is this a lot less stable with a formal charge, but also there's a significant resonance contributor here where the positive is distributed a lot to the carbon as well as the oxygen, and that will really help to attract in the otherwise relatively weak nucleophile, the water molecule. And so if that comes in, now since this was a step that was slowing the attack down, right? We couldn't get the water to come in here reasonably often because of how high the activation energy is and how unstable the first intermediate is compared to the reactants. But now my nucleophilic attack step of the process has a positive charge already, so it's already pretty high in energy. And when the water attacks it, the next intermediate we would draw, there's already a proton here. So when the water comes in, there's only one formal charge, one positive here on this oxygen. And so it's not really that much more unstable than the positive over here. This one's stabilized by resonance and this one is not, so it's definitely going to be higher in energy for the intermediate than the reactant. But I mean, the activation energy is much more reasonable. So by adding an acid and protonating the carbonyl, it lowers the activation energies for the subsequent steps and allows this reaction to occur. So we can imagine a nucleophile, even as weak as a water, coming in here and attacking and eventually producing a product. So what would the product be? Well, it's not stable yet with a positive here, so we would have to have another water molecule come in there and pick off that proton, and that would give me something like this where I've got a diol, two OH groups on the same carbon. And that functional group isn't a typical diol. Right? Normally we have at least a couple carbons between OH groups of a diol. These two OH groups maybe behave independently. But here, since the two OH groups are on the same carbon, now, if one were protonated and made into a leaving group like this, which would just go back, and since there's acid around, that could definitely occur. The other one could easily swing its electrons in and push that out, which would go back here. And then maybe this water would pick off this proton and go back here. So that means this whole process is easily in equilibrium. Right? And that's generally true whenever our activation energies aren't that high and we have multiple steps involved. It can go forward, it can go back, unless there's a key step that is extremely favored in one direction over the other. Often we get these equilibrium. So we have to figure out how to control this equilibrium and shift it toward the direction we want. Predicting whether the nucleophilic attack is product or reactant favored is a little different, obviously, from predicting whether the overall process is reactant or product favored. So we are going to talk about whether the overall process favors the product or the reactant, since it can shift back and forth in equilibrium. But if we're just looking at the nucleophilic attack, which is this step here, where the water attacks the carbonyl, that one is probably reactant favored. And that's why it's still the slow step of the process, right? Because here we have the positive stabilized by resonance, and we have two molecules with a fair amount of entropy that can move independently with a fair amount of variety, versus after the attack, now my positive is not stabilized by resonance on this oxygen, and the two molecules that were able to have more variety acting independently are now combined into one, so there's less entropy as well. So in this key slow step of the process, the free energy goes up because the positive is less stable and there's less entropy during that step. But it's not so much that it can't happen kinetically, that's the key. All right, so we showed those steps over here. If water were to attack a carbonyl, it would probably only happen reasonably often if the carbonyl were already protonated. Then the water could attack and give this intermediate, and then the water would deprotonate this and give this product here. So will the overall process be fast or slow? It's actually going to be relatively fast if there's an acid catalyst. So we'd say without an acid catalyst, it's going to be quite slow. And again, the reason for that is because without an acid catalyst, when the water attacks, forming two charges, this is a really pretty unstable intermediate, not very high energy intermediate, versus a much lower energy reactant. So the activation energy for that step is pretty much prohibitive. Will the overall process be product favored or reactant favored, right? So this is a thermodynamic question. And I should probably be more careful when we're going through this because I really want you all to be able to distinguish between thermodynamics and kinetics. If we're talking about individual steps of a mechanism, the activation energy, the transition state, that's all kinetics. How often something will occur is kinetics. But if we're looking at thermodynamics, thermodynamics is about analyzing the overall process. And so we're going to also take a look at that over the next couple slides. All right, so here are some equilibrium. We said this process can shift back and forth. Typically, it's done with an acid catalyst. Also, to point out real quick, the acid catalyst only helps the reaction kinetics, not the thermodynamics. So adding the acid catalyst lowers the activation energy, allows the steps to occur more often than without, but the overall delta G value for reactants versus products is not affected by the presence of the catalyst. So we don't have to factor the catalyst in if we're looking at what side of the equilibrium is favored in this reaction. And what you can see is it depends on the substrate. Sometimes when I react water with the substrate, I get a reaction that's very reactant favored, right? This is like 99.9% of the material exists on the reactant side. Other times, with different substrates, reacting water, giving this diol where the two OH groups are on the same carbon. Sometimes that's product favored. Here, more than 99% of the materials on the product side. And so there are a few factors that affect this process. I want to talk about them so you can have the ability to predict which side of an equilibrium would be favored in these reactions. So the one factor that's very important here is entropy. And we know since in each one of these examples there's 2 moles of reactants and 1 mole of products, which basically means that we're combining these two and joining them together. It's an addition reaction. We're doing nucleophilic addition across a carbonyl. And we know addition reactions combine 2 moles to 1, so there's a decrease in entropy, a negative delta S, and that disfavors the product side, right? We know the universe favors the side with more entropy because those particles have more variety in the ways that they can move and be positioned in space. So that's one factor. If that were the only factor, obviously all these equilibrium would favor the reactant side rather than the products. Another factor that's not listed here, which definitely should be, is the bond enthalpy. So if we're talking about bond enthalpy, what is happening here on net is a pi bond is getting converted into a sigma bond. Right, so we have to break this pi bond. We also break a sigma bond in the water, but then we're forming two new sigma bonds. One is actually between the OH and one is between the CO. So breaking a sigma bond, forming a sigma bond, that's basically about the same roughly, but pi bonds aren't as stable. So based on the fact that we're breaking this pi bond, we only have to put a little energy in to do that, and then we get to form a new sigma bond that's lower in energy or more stable. The value for delta H is going to be negative. It's going to release energy. And so from that factor, that would suggest it to be product favored. So we have a competition here. What's more important, the entropy favoring the reactants or the enthalpy favoring the products? And here are a couple more factors that affect the enthalpy. Let's look at sterics. So the main difference between these two reactions is sterics. Not the only difference, but the main difference, right? I've got these two methyl groups here, and they're creating a little steric hindrance. In the carbonyl form, there's very little steric hindrance. But when I bring a water in here and go from an sp2 hybridized carbon where the bond angles are 120 to an sp3 where the bond angles are 109, everything's a little bit closer. The sterics created by these methyl groups bumping into the OH groups a little bit. There's going to be potentially some torsional strain depending on the rotational conformation that could occur here. That's going to make it a little bit less stable. Compared to this reaction where I've got these two tiny protons here, they don't really take up much space. So when I have larger groups, the reaction favors the reactant side because the products are a little bit extra steric hindrance, creating some repulsion. And so that means pretty much almost any R group I have here, when I react that with water, it's not going to form this product very much because the equilibrium due to the sterics is going to favor, and the entropy is going to favor the reactant side. In the case of the formaldehyde, since the product has so little sterics, the fact that we're going from the pi bond to the sigma bond is what helps the products be more favored in that example. So then, lastly, when it comes to induction, we're talking about withdrawing electrons from the carbonyl carbon. Right, so here, in this example, the difference between 1 and 3 is a difference in induction. Here I've got methyl groups creating some steric hindrance. Here I've got CF3 groups, which are similar in size to the methyl group, so they're still going to create some steric hindrance, and that makes the product a little less stable. But in this case, the product is still greatly favored, and so that's compared to the reactant. So because these fluorines are all pulling electrons away from the carbons they're directly attached to, creating very large partial positives there, that will attract electrons away here, and there's already electrons being attracted away from the carbonyl carbon by the oxygen. And so this creates a very large partial positive on that carbon. And that makes it a little bit less stable. It's a lot of charge on one atom, almost as much as a formal charge. So it's pretty unstable. And so by bringing the water in there and attacking through the mechanism and eventually producing this product, here we've got, we don't have quite as much partial positive on that carbon. So the product is favored because the sigma bond is more stable than the pi bond, and because the reactant is especially destabilized by withdrawing electrons away from the carbonyl carbon. And that the CO double bond withdraws electrons from the carbonyl carbon much more than these two OH groups because of the resonance as well. So when I already have resonance and induction pulling electrons away and creating a very large partial positive, which I don't really have the same over here. Here I just have a little induction. The extra induction of the CF3 groups really affects this molecule a lot, destabilizing it, and that shifts equilibrium to the product side. So there's a lot of factors involved there, and you want to be able to discuss how each one affects the equilibrium, right? So you can imagine an exam question here where I would ask you to describe like 4 factors that affect these equilibrium and predict which side each factor favors. Right? So we know the entropy favors the reactant side because there's more moles on that side. The enthalpy generally favors the product side because you're converting a pi bond to a sigma bond. But depending on the sterics and the induction effects, the product side might be disfavored by sterics since it's more crowded, and the reactant side might be disfavored by induction if there's too much partial positive on the carbonyl carbon. So how can we get this reaction to work? There are really two options. One is to catalyze it with a base. So by starting with a relatively unstable negative charge, we're starting relatively high in energy. So when that attacks and pushes electrons up to the carbonyl, I have another negative. So either way, I've got a negative to begin with, or I've got a negative that I'm forming. Here, the negative is probably a little bit better solvated by solvent since it's smaller than over here. But they're probably similar in energy. So that first step, again, it doesn't require very high activation energy if the two sides of that reaction are similar in energy because they have similar quantities of unstable negative charge. Then if that negative picks up a proton, that regenerates the OH minus, that's why it's a catalyst, and it also produces the product here. And in this case, delta G is going to be negative because we just saw in the last slide that with this particular reactant and water, this product is the favorite product because we're converting the pi bond to the sigma bond, and there's not too much sterics to disfavor the product side, so the product's slightly lower in free energy than the reactant, giving us a product favored process. So that's one option, using OH minus as a catalyst. There's the full mechanism there. How does it increase the rate of reaction? It lowers the activation energy, and it does so by creating similar free energy for the reactant, negative charge, and the intermediates, negative charge. And because these two are similar in energy, as we showed here, it doesn't take a large activation energy to get from one to the other. The presence of the OH minus does not have any impact on the degree to which the process is product favored, right? Whether it's product favored, that depends on delta G, and that's a thermodynamic question. And that depends on a comparison between the reactants of the reaction and the products of the reaction. It does not depend on the catalyst because there's the same catalyst on their products, and reactant side basically cancels itself out in the net overall reaction. So you want to keep in mind the catalyst affects the kinetics, but not the thermodynamics. So the other option for this reaction, which is basically a hydration of a carbonyl because we're adding the components of water, we're adding a hydrogen to one side of the pi bond and an OH to the other side of the pi bond. So the other option is to do an acid catalyzed hydration. And so here we're using water and H3O plus, so some kind of strong acid, protonating water, converting it into H3O plus. The carbonyl will easily pick up a proton. So if we're looking at the reaction coordinate diagram, this first step would be slightly product favored because the resonance here can stabilize this positive better than the positive over here can be stabilized. Then the water attacking creates another intermediate. That one, this is going to be the slow step. That one is probably not as stable. So there'll be a higher activation energy there, or a higher transition state energy there than in the previous step. The attack there creates more sterics. It's a decrease in entropy. And so that's not really a favorite step. Also, the positive here is no longer stabilized by resonance like it was there. But then deprotonating that helps to form the product. And as we said, the overall product here, due to the sigma bond versus the pi bond, and due to the fact that the carbonyls, or that there's not much sterics here, we get a net overall negative delta G for this product favored reaction. The key here, though, is by using the acid catalyst, we don't have to go through any especially high transition states, right? Even though this step is not product favored as a step, the activation energy barrier there isn't very big because I've already got a relatively unstable compound. Their energies relative to one another are not that different. So there wouldn't be a very high peak in between those two intermediates. And so by facilitating that step, the acid catalyst facilitates the overall, how often the overall process will occur, but the catalyst itself does not affect the initial or final energies in the equilibrium. All right, so we just explained that. Will it make the process more product favored? No. The equilibrium is not affected by the catalyst. All right, so that's pretty much the details associated with water acting as a nucleophile. And since water is very similar to alcohol, we could imagine a very similar process where the alcohol acts as a nucleophile. There's going to be more sterics here, but we could easily imagine this oxygen attacking the carbonyl. So in this case, since the alcohol and the carbonyl are neutral to begin with, the attack's not very likely, right? So we already talked about that, how a weak nucleophile that's neutral, if it were attacking and pushing electrons up, I get a negative here. This oxygen would form a positive. So forming two formal charges in one step from two neutral compounds has a pretty high activation energy. That wouldn't happen very likely. So this is why we have a proton. This is a catalyst. It's going to start the process off by protonating this. And now that positive is going to really help to bring electrons up. And that will help to allow the alcohol to attack. So we still have an equilibrium. We'll take a look at the complete mechanism on the next slide. It's a lot of steps. And in the process, we want to make sure we analyze how the catalyst helps this reaction work. So the key thing about the catalyst, the main thing about how the acid catalyst allows the reaction to proceed, is by getting the slow step to happen more often, right? So this attack of the nucleophile on the carbonyl carbon is a slow step. And by putting the positive here, it raises the initial energy versus what it would be if it were neutral. It allows the attack to occur without forming an intermediate that has two formal charges, so the next intermediate's not that much higher than the initial one, and that allows the reaction to occur without an extremely high activation energy, right? So the same thing we were saying before. So here's the full mechanism for that. And this is one that I might ask you to draw out. So here A is just representing a generic acid. You could write this as H3O+. You could also just write it as H+, but technically you wouldn't have free H+ in solution. So that's kind of taking a shortcut, but I'm okay with that in this instance. So if a lone pair picks up a proton, you could show it that way. You could show it picking up a proton from H3O+ or some other strong acid, that would be fine. If it picks up a proton, that creates a positive charge, right? So this is the key slow step. That's a step that starts the process off here. The alcohol attacking there, pushing electrons up to the oxygen, produces a relatively unstable positive because of the sterics here, and because there's no resonance to stabilize it like there is over here. Then you might have a water, the conjugate base of the acid, depending on how strong it is, might get involved, or maybe another OH, or maybe another of the carbonyl. So we don't know exactly which of these bases is going to pick this proton off, but one of them will pick up that proton, and that gives you something called a hemiacetal. So this is relatively stable. There's no formal charge, but there's some sterics there. And we still have lone pairs that could pick up another proton. So also keep in mind, all of these steps are equilibrium. If we look at every one of these, it's an equilibrium. It could go forward or backward. And when we have an acid around, we have to keep in mind that the proton's basically randomly being shuttled around from one structure to another, in really not a controlled way, in a pretty random way. So any one of these lone pairs could pick up that proton. If the oxygen here picks up the proton, we go back. If this oxygen picks it up, we go forward. And so we can always go back or forward at any time, depending on which one happens to kind of randomly pick up a proton. If the OH picks up the proton, it makes it a leaving group. So this oxygen can swing in and push that out. And this process, this step here is pretty favored because we're going from 1 mole to 2 moles. We're producing water and this. And so that is favored by entropy, that particular step. But now that we have a positive here, it's susceptible to another attack. After that attack, a proton transfer can give something called an acetal. Right, so if you look at the mechanism, it's very easy to see each step in the forward direction could readily occur. There's no one single intermediate that's especially unstable. All of the attacks and proton transfers look reasonable. But that could be said both for the forward and reverse reaction. So kinetically, this mechanism is nice. It allows the forward reaction to occur, but it also readily allows a reverse reaction to occur. So we want to look, one point I wanted to make about that is this step here. Let me just get rid of some of this red so I can point it out more clearly. This key step here is one that students often draw incorrectly, so I just wanted to focus in on that and make a point about it. You would not want to show it this way, right? So there's too much steric hindrance here for this nucleophile to attack directly. So that's one important point about that. So if we're looking at the mechanism, right, this nucleophile attacks in this step because the carbonyl is pretty much wide open. It's sp2. There's nothing above or below the plane to block this from bringing its orbital and orbital overlapping and forming a new sigma bond there, right, this new sigma bond. We can't have it attack here and push out the water leaving group though because there's too much sterics. Even if the sterics weren't an issue though, even if these were hydrogens, we still wouldn't see this attack. And that's just simply because the collision is not as likely as this swinging in and pushing the leaving group out. So this can collide with anything, the solvent, the container, as long as it collides with enough force to bring in these new electrons and break this bond and go forward, that collision is going to produce the product. In order for this to attack, it would have to be a very precise collision from the back side of that leaving group. It's just not going to occur nearly as often. So that's why we see this as an intramolecular loss of the leaving group. We're not seeing intermolecular. It's not between molecules. It's not a molecule coming in. It's within the structure. It should be the lone pair on this oxygen that swings in to form a pi bond that pushes the water leaving group out. Intermolecular steps unlikely, 1 because of sterics, and 2 because the intra is faster, or actually I shouldn't say that. It happens more often. Actually, probably better to say is a more likely collision, much more likely collision. Right? Because intramolecular collisions don't require any specific second structure to collide in a specific way, and a backside attack, it's just quickly shift those electrons in and push out the leaving group. All right, so as we were saying, these are all equilibria, all of these acetal reactions, and most of them are reactant favored. So I really have to get to a situation where I have almost no steric hindrance. I have to pretty much start with formaldehyde. If I put an R group at either one of these positions, it's going to create sterics here with these ethoxy or even whatever alkoxy groups these are. It's going to create a lot of sterics between those and the R group, and that would shift back toward the reactant side. So it's only really product favored if I've got hydrogens here, which is really limiting in terms of how often I can do this reaction. Right? There's almost no other carbonyl where this reaction will be product favored. So almost no matter what my R groups are, if they're not hydrogens, it creates a lot of steric hindrance between all this stuff, and that will shift back toward the reactant side. So what else is affecting the equilibrium here? Another thing that's affecting the equilibrium is entropy. In these first two reactants, I'm starting with 1, 2, 3 moles, because there are 2 of these that have to react. 3 moles of reactants, 1, 2, 3. And I'm producing 2 moles of products. So it's not as stark as 2 moles combining to 1. I'm not decreasing the number of moles by half, but it is a decrease in the number of moles or particles or molecules or chemical units that can bounce around, so there's less variety on the product side. And so that's another reason why it's generally reactant favored. Now going again from the pi bond to the sigma bond makes it more likely it could be product favored. That's the main reason why this first reaction is product favored. But with the entropy favoring the reactants and a lot of sterics over here favoring the reactants, most of these reactions don't work because they're reactant favored. With the exception of 5 and 6 membered cyclic acetals. If we look at the equilibrium here, there's a key difference. Instead of starting with 3 moles of reactants and making 2 moles of products, we're starting with 2 moles of reactants and making 2 moles of products. So here, for cyclic acetals specifically, delta S is going to be close to 0. So we'll take out the entropy part of it, which was favoring the reactant side, and now it's favoring both sides pretty evenly because there's equal amounts of moles on both sides. Now the products do form a ring, so maybe we could predict that there'd be a little bit less entropy because there's some rotational freedom limited by this ring compared to what we have over here. So we might be able to say, well, maybe delta S is slightly negative, but probably not by much. And so then this ends up being a situation where the instability of the pi bond versus the new sigma bond that forms actually favors the product side. So here's a reaction you can do. If you want to form a cyclic compound that's also an acetal, meaning it has 2 oxygens or 2 OR groups bonded to the same carbon, then you can do this reaction. So we talked about entropy, we talked about sterics. Let's talk about the other 2 factors. Induction, so that would be, again, if you had on this carbonyl side, maybe something very electronegative, like a CF3 group. I can't put a fluorine right here because it's also a leaving group and that changes a lot of the chemistry, but if I put the fluorines on one more carbon away, then I'm just looking at the induction, the effect of them pulling electrons away, creating these large partial positives, which attracts electrons away from an atom that already has a lot of electrons attracted away from it through both induction and resonance. That's going to create a very unstable big partial positive on this carbonyl carbon. Since that's unstable, it would help shift it toward the product side. Right, so we talked about that already, but just want to point that out again. And then here's a new one, Le Chatelier's principle. Right, so this is true for these other mechanisms we saw back here. Right, generally, anytime I've got a bunch of steps in equilibrium, I can shift it all the way to the product side if I use a large excess of one of my reactants. or I can shift it back to the reactant side if I use a large excess of what one of my products would be. Right, so if we're looking at the net overall reaction here in the equilibrium, and we're talking about Le Chalet's principle, we could say if I add excess of the alcohol, it would shift it toward the product side even more than would normally shift to that side. But if I add a large excess of water, it would shift it back to the reactant side. Right, so I can also control this experimentally by adding water or adding alcohol. And generally what that means is if you want to make the product, you'd use alcohol as your solvent. If you want to make the reactants, you'd use water as your solvent. And since these cyclic ones don't have the entropy cost associated with making the product that the other ones have, that's an especially useful situation where if you use excess of the diol, it'll help shift that equilibrium to the product side. But since water is a product, if you use excess of that, it would shift it back to the reactant side. So that means these reactions are controllable. We can control which side the reaction goes toward depending on how we set the reaction up and what we use as our solvent. And so that's what this is demonstrating here. Either way, I need the acid catalyst to get through the mechanism kinetically, right? So just to point out, the catalyst is there for kinetics. It does not affect the equilibrium. It's not going to affect which side is favored once it reaches equilibrium. But I need the acid to be a catalyst so that it will reach equilibrium in a fairly quick amount of time. Otherwise, if I just put these together, it's going to take days and days and days to get to equilibrium. That's not a practical situation. So if I want to form the carbonyl and the diol, since water is my product, I would add lots of extra water and an acid catalyst, and that would shift it back toward the reactant side. If I want to make the acetal, then I add a large excess of the diol, since that's a reactant, and that shifts it toward the product side. Another possible strategy there would be to remove the water as it forms. So there'd be some way to remove that, maybe add like a drying agent potentially or something to absorb the moisture. Well, that might absorb the other reactant, so there'd be some experimentation necessary to figure out exactly how to do that. But theoretically, if you remove a product as it forms, it'll help shift the reactant more toward that product side. So if I use more water, it'll shift it back to the reactants. If I use less water, or instead I use the diol as my solvent, especially, that would be a large excess of reactant, that would shift it toward the product side. All right, so that now gives us the ability to answer the first quiz question. So again, the proton there is used specifically to protonate this compound to make it kinetically more feasible for it to be attacked by a weak nucleophile. That creates a formal positive there. It makes the resonance contributor where these electrons swing up much more significant. It raises the energy so that when this alcohol or diol attacks from any one of these four lone pairs, it can produce an intermediate that does not have two formal charges that would go through a really high energy transition state. So if these electrons swing up, now I have two lone pairs on that oxygen, and this oxygen now is bonded to that carbon. So the advantage of this step is you're forming a pi bond into a sigma bond. The disadvantage is you have a positive that's not stabilized by resonance, and you're going from 2 moles to 1, so it's an entropy cost there. So then what some students want to do, which is not really correct, is to, I know it's nice if it will work because it would be fewer arrows, you wouldn't have to take the time to draw as much stuff into your mechanism, but doing this is not going to work because this oxygen is 1, 2, 3, 4 atoms away from that hydrogen. It's not enough. It's, in a way, you could think of it as being too close. But basically what we're talking about here is if an oxygen is going to use its lone pair to do something, and it's going to do it to an atom that's 4 atoms away, in order for it to grab that proton, they have to be close enough, right? This proton's nucleus has to be, and its 1s orbital has to be close enough to this oxygen's lone pair orbital to orbital overlap to make a nucleovalent bond. In order to do that, the angles here have to be pretty close to 90 degrees, and that creates a lot of angle strain. So we're not going to see that. Right? The molecule is not going to adopt a really high energy angles with all this angle strain to transfer that proton, when there's plenty of other ways to transfer a proton and collisions that will facilitate the proton. So what would happen here is this oxygen would pick up a proton from the acid catalyst, and probably this molecule, since it's the solvent, or maybe another one of these if it hasn't reacted yet, would pick up this proton. So we could show, either of those doing that. Pick up that proton, electron swing in here. So those two proton transfers wouldn't necessarily occur at the exact same time, but if you want to show them both so you don't have to redraw the whole structure, that's fine. I've got no problem with that. So now this oxygen's protonated. And again, all these steps are reversible. There's no reason why one oxygen has to be protonated and another is going to be deprotonated. The protons are always going to be swapped back and forth, creating all these intermediates. So we got 3 more carbons here. Oops. 1, 2, 3, 4 each. So now that we have a water-leaving group and this oxygen is no longer protonated, my positive is up here. So again, we could imagine maybe this oxygen down here swinging all the way up in there. That'll be 1, 2, 3, 4, 5, 6 atoms away. That collision could occur, but since there's a fair amount of sterics here, and it would have to occur just from the backside attack perfectly for it to work to push out the water, it's more likely that this water would just leave upon any collision that has enough energy to break that bond. And then this oxygen could swing electrons down to help balance out the noble gas configuration of that carbon. So that would give me the next intermediate. This electron swing in here, so now I have a double bond there, stabilizing the positive charge through resonance. So now this carbon here is sp2. Before it was sp3, and so it's hard for the nucleophilic attack to occur there. But now that it's sp2, it's flat, it's much more open sterically, so this nucleophile can very readily come in there and form a 6-membered ring, pushing electrons out here. This oxygen here is still protonated, so we need one more step. Something will deprotonate this. It could be another molecule that hasn't reacted yet. Probably be this, since if we want this equilibrium to be product variable as possible, we would use a large excess of this, making it our solvent. Since it's a reactant, it would shift the equilibrium forward toward the product side. Technically, these should all be shown as equilibrium arrows. So this molecule we could show it picking up this proton, these electrons staying behind there, and that would give the acetal, cyclic acetal product. And since there's no real big entropy decrease like there was when we formed other acetals, because we're starting with 2 moles of reactants and we're forming 2 moles of products, including this and the water leaving group that leaves, we can favor the product side because it has a sigma bond versus a pi bond without a major entropy decrease. So since acetals, as we were just showing, can be formed as cyclic acetals, and they can go backwards through the same mechanism, just reverse. That means we can control whether they're put on by using an excess of the diol. We can also control them being taken back off. If we have excess water, and this oxygen picks up a proton, it would go back here. If we have excess water, then this electron pair could shift in and push that leaving group out and go back here. Then it could be a water that attacks there to push these electrons out and go back again. And since that's a product, if I add an excess of it, it'll help collisions occur there and help shift the equilibrium back both kinetically and thermodynamically through Le Chatelier's principle. So you can make a cyclic acetal using excess of the reactant. You can remove the cyclic acetal using excess of the water. And so that means that acetals are often used as protecting groups or protective groups. We can specifically protect aldehydes and ketones, right? So acetals won't form on esters or carboxylic acids or other carbonyls that have a heteroatom bonded to the carbonyl carbon. But if the only thing bonded to the carbonyl carbon here is another carbon or a hydrogen, then you could add either a 2-carbon diol with an H plus, and you'd use excess of that, or you could add a 3-carbon diol with an H plus catalyst. Either of those would react selectively with the ketone in this case versus the ester, and they would both give a cyclic acetal, leaving the ester as is. So this CO double bond would be converted into a 6-membered ring if I use 3 carbons in that chain, or a 5-membered ring if I use 2 carbons in that chain. So that would be step 1. Protect the ketone or ester, making a cyclic acetal. Step 2, how do I convert this ester into this alcohol? That would be LAH. LAH would deliver a hydride here. It wouldn't deliver it into the acetal carbon because it's now protected, right? A hydride's only going to attack a carbonyl, and I don't have a carbonyl here anymore. So the hydride would attack this carbonyl or this one here. It would attack that, swing electrons up, and when they swing back down, it would push out the OR group, and then another hydride would attack, and that's how I would install 2 hydrogens there. And so then in the third step, I would add H plus and water. The H plus would serve 2 purposes there. It would pronate this oxygen, right? Because when the second hydride comes in here and pushes electrons up, I get a negative on that oxygen. So it needs to pick up a proton. And I'd use excess water because that would deprotect the cyclic acetal. And we just saw that happen in the forward mechanism for that on the last slide. The reverse mechanism would be the same, except for I'd have water attacking. So each of these oxygens would one by one get protonated to make a leaving group, and then they would leave and water would replace them. And then that would form the CO double bond. So that's how I get the CO double bond back. So here's a reaction sequence that utilizes this chemistry to convert this first molecule into this product over here, which is also an acetal. So make sure we understand how to get through this type of question. So here I have a 2-carbon diol. I'm removing water, which would be similar to saying that I have excess of this. That would help shift this toward the product, forming a cyclic acetal at the carbonyl carbon, not when there's a heteroatom attached, so this one would not react, but this one would. So the first question mark here, let's call this A, B, and C, just keep track of everything. A is going to look like this. So the ester is going to remain unchanged right here. But then bonded there, I've got the CO double bond, and that is going to be converted into a cyclic acetal with 2 carbons between the oxygens. So that would be A, the product of the first reaction here. So then how do I convert that into this compound? Well, I know I can remove the cyclic acetal and get the carbonyl carbon back if I use H2O and H+, which I could also just write as H3O+. But it's nice to write this way because then I can say excess will really help shift that equilibrium back toward the carbonyl side. So these reagents would convert this cyclic acetal back into the aldehyde group. But I obviously don't want to do that first, because what will be the point of putting it on and then taking it off immediately? What I want to do first is to react this ester group with whatever is necessary to open that up. And that is LAH. So I would use excess LAH. And again, LAH reacting with an ester, just show that, right? The lithium aluminum hydride, the hydride comes off the aluminum, pushes these electrons up. So I'm just going to show this part of the structure. So now there's a new hydrogen there. Right, the hydride comes in, pushes electrons up. Then these electrons are going to swing back down and push this oxygen out. So we need excess LAH because another hydride is going to come free from the aluminum and push these electrons out. So this part of the structure I have 2 hydrides delivered to it. It's going to give me a negative oxygen. This part of the structure over here, once that oxygen here is formed into an OH, it's actually going to be deprotonated by a hydride. We know lithium aluminum hydride won't work in the presence of moisture because it's reactive toward protic compounds, and this OH is protic. Right? So what's going to happen there is a hydride from the aluminum is going to pick off this proton, and that's going to give you a negative there. So both these oxygens would remain negative, which basically produces this product once they get protonated. And so step 2 provides the proton both to protonate these oxygens and to act as a catalyst in the removal of the acetal, the cyclic acetal group to reform the aldehyde. So then what do I need here in step C? Right, so one thing I can do here is count my carbons. 1, 2, 3, 4, 5, 6. So I've got 1, 2, 3, 4, 5, 6. So I'm not changing the number of carbons. I just want these two oxygens to both connect here at carbon 1. And so the oxygen that's connected to carbon 4, it needs to swing around and connect to carbon 1. And the oxygen that's bonded to carbon 6, same thing, it needs to swing around and bond to carbon 1. So that's basically intramolecular cyclic acetal formation. So it's the same mechanism we've been talking about. We just need a proton source. We don't want to add lots of extra water or any other alcohol. We just need a tiny bit of acid catalyst to protonate this carbonyl so it'll produce a positive that's stabilized by resonance. Then these oxygens will attack. One will attack, then it'll be deprotonated to become neutral. Then this oxygen would get protonated again to make a water-leaving group. This oxygen's electrons would swing in and push that out, and then this oxygen would attack, and we would have them both connected there once they're deprotonated. So I know there's a lot of details in this mechanism. It's a long mechanism, so that just means you might have to do a little extra practice to really master it. All right, so that is it for oxygen attacking a carbonyl in the form of water, or in the form of an alcohol, or in the form of a diol to form an acetal or a cyclic acetal, or a hydrate if water is a nucleophile. So now we want to look at what happens when a nitrogen nucleophile is around, like an amine. So the first question is, are amines better or weaker nucleophiles than water? All right, if we imagine water attacking as a nucleophile some carbon versus a nitrogen of an amine attacking a carbon, well, if the water attacks, I'm going to have a positive formal charge on the oxygen. If the nitrogen attacks, I'm going to form a positive formal charge on the nitrogen. Because oxygen is more electronegative, it's not as stable with a positive charge. It's going to start pulling electrons away, including from the carbon. It might just leave. Versus the nitrogen, which is a little lower in electronegativity. It doesn't rip the electrons back from other atoms so strongly. And so because we have a lower electronegativity atom, it's more willing to share, and that makes it more nucleophilic. So as the nucleophiles go, amines are stronger than water. Even though they're stronger than water, we still need a catalyst, because we still have the same issue where if I have a carbonyl compound and I'm experimenting with the possibility of an amine attacking that compound, if I don't have a catalyst, it requires two neutral reactants to form an intermediate with two formal charges. And the kinetics associated with that are not good. We're starting with substances that are pretty low in energy and forming something that's pretty high energy. It's not as high in energy as it would be if we had two oxygens, because an oxygen with a positive is less stable than a nitrogen with a positive. But still, forming two formal charges from no formal charges requires a lot of activation energy. So it's not going to happen very often. So we're going to do the same thing we were doing before, and that is to use an acid catalyst. The base is not going to work. What made the base work before was that it could work as a nucleophile and attack directly, right? But that's obviously not what we want here. We want to try to see what kind of compounds we can make if we have a nitrogen attack. So we don't want some other nucleophile around. We just need an acid to start by protonating this. So it'll already be kind of unstable. Then when the nitrogen attacks and swings electrons up, it'll already be protonated. And so we'll have an intermediate that's much more reasonable. Now I only have a positive on the nitrogen here. So let's look at that in a little bit more detail. So what are these products going to look like? I want to keep in mind the effects of entropy on the process for when we combine two molecules into one. Right? So if we go with an analogy similar to the reactions we were just looking at, we could imagine the carbonyl compound. Right, we just saw it react with alcohol. We said if we have 2 moles of alcohol, especially if the two OH groups are attached to the same molecule, then we just have 2 molecules reacting. But if they're 2 separate molecules, we need 2 of those. The alcohol would have to attack. Water would be protonated first, right? The whole mechanism we already saw, and that would produce this product and a water. So we went from 3 total moles to 2. And we said the entropy cost there makes that reaction less likely to occur, right? We said when these reach equilibrium, they pretty much always favor the reactant side. Unless we have so little sterics due to these being hydrogens, then it's going to favor the product side. So there's really not much variety there we can do. If we've got R groups here, this reaction is not going to be favored. We did say, though, that the reaction could be favored specifically if we have a diol with 2 or 3 carbons between the OH groups, because then I only need 2 moles of reactants. Is that one reactant has both OH groups that I needed up here, and that would produce a cyclic diol. And if there's 2 carbons here, it's a 5-membered ring. If there's 3 carbons here, it's a 6-membered ring. And that produces water. So we said, in that case, since the number of moles isn't really changing, the process is more of an equilibrium, and since we're going from a pi bond to a sigma bond, it's actually going to be mostly product favored. So we figured out how to make that work by taking away the fact that entropy makes a reaction normally favor the reactant side. So I want to expand that discussion and talk about what if we had a nitrogen nucleophile. So we could imagine the same thing. We could imagine a CO double bond and 2 amines. The amines can have hydrogens or R groups. And we could imagine forming something like this once the full mechanism takes place. If we used excess of the amine, it will help drive it forward. If we use excess water, it will help drive it backwards, so we can still control the equilibrium with Le Chatelier's principle. But here we do have the fundamental problem where I've got 3 total moles on the reactant side and only 2 on the product. So the fact that entropy disfavors processes where molecules combine to form fewer molecules, what actually is going to happen here is a different reaction that will yield a different product that won't have less entropy than the reactants in this way. So let's take a look at the mechanism, and that will help us predict why we're getting the products we're getting. All right, so very similar to the mechanism we already saw. Lots of steps, but a lot of the mechanisms in this section are very similar. So if you practice them enough, what you're practicing should really help you learn most of them in this section fairly well. So what's happening here? I've got an amine nucleophile. I've got a carbonyl. So if I don't add a catalyst, I could imagine the nucleophile attacking, pushing these up, but then I get 2 charges on one structure. So probably this mechanism is showing things not quite in the most likely order that would occur. So probably what would happen first would be this oxygen would pick up a proton from the acid catalyst. It would already be protonated. Once it picks up a proton, and some of the molecules could go through the pathway that was already shown here, but if this oxygen picks up a proton, and as we said, the protons will be shuttling back and forth, maybe the nitrogen picks up a proton, and then maybe the oxygen picks that proton up off the nitrogen. Because it can be resonance stabilized, it's not unreasonable to expect this oxygen to pick that proton up. Then the nitrogen can attack here. The oxygen's already protonated, so when the nitrogen attacks, I now have only one total formal charge on my structure. And that's what we have here. So then the nitrogen's unstable with a formal charge. So the best base around, which may be the conjugate base of the acid, it might be more likely to be a fresh amine because nitrogen is pretty good at sharing its electrons. So that might be actually what picks up that proton more likely, leaving electrons behind. And this forms a carbonylamine. This is also called hemiaminal, similar to a hemiacetal that we saw. So this is a problem this is a product you might have envisioned forming, but one, as we said, if you're combining two molecules to make one, that's probably not going to be that favored by entropy. And since there's still acid around, and catalyst is always regenerated, there's always going to be acid in the solution, the equilibrium is going to keep going until it finds the most stable situation, which creates the most entropy total for the universe. So if this oxygen picks up another proton, it can make a leaving group. The nitrogen can swing electrons in, push out the leaving group. One of these should be a proton, not an R group. When the nitrogen swings its electrons in to push out the water leaving group, that produces this structure. And then probably, as we said, the best base around would probably be the amine. Pick up that proton. It could also be another carbonyl, but picking up that proton then produces what's called an imine. An imine is like an amine, but an amine has single bonds for the nitrogen and whatever carbon groups are attached. An imine has a double bond between the nitrogen and the carbon groups attached. So the advantage here is, in this step, the nitrogen swinging its electrons in and pushing out the oxygen to produce this intermediate, it produces a water. So the overall net reaction, where the carbonyl reacts with the amine to produce the imine and a water, 2 moles of reactants, 2 moles of products. Pi bond on the reactant side, pi bond on the product side. Very similar. So the equilibrium here comes down to favoring whichever side Le Chatelier's principle predicts. So if you wanted to make more product, you'd add a large excess of amine to this carbonyl and it would shift toward the product side. If you wanted to take that amine back to the carbonyl, you would add a large excess of water and it would shift the equilibrium back to the other side. Let's talk about the acid catalyst. The optimal pH for this reaction is about 4 or 5, right? So we can see the rate of reaction, or how often the product is produced, is pretty slow at low pHs. It's also pretty slow at higher pHs. The intermediate pH is slightly acidic, so that gives us some extra H plus in solution. That really is a catalyst, but we don't want it to be too acidic. Right? So the idea here is, why would the pH below 4 start to really decrease the reaction? And the answer to that is in the mechanism. If the pH is too low and there's too many protons around, then this nitrogen gets protonated and the oxygen gets protonated. And so if the pH is too low, because there's too many excess protons around, then not only will the carbonyl be carbonated like we want to make it more electrophilic and have the nitrogen attack, but the nitrogen will be protonated for almost every molecule. And if it's protonated, it's not a nucleophile. Can't do a nucleophilic attack with a molecule that has no electrons to share. So it has to have the lone pair there. At least some of the molecules, some can be protonated, but at least some, as long as some have a lone pair, then they can attack. But if the pH gets too low, then pretty much all these get protonated and the reaction won't work. pH above 5 means there's too little H plus to really help as a catalyst. Right, so we need some H plus, so there'll be enough shuttling back and forth that once in a while, or fairly often at least, this protonated structure will bump into this unprotonated structure, and the nucleophilic attack that we need for the slow step of the mechanism can occur. All right, so we're just fine-tuning the amount of H3O plus or the amount of H plus in solution to facilitate the mechanism in its ideal way. All right, so let's go back and check out the mechanism here. So we showed how this would work if we had a primary amine. A primary amine is one that has only one R group directly attached to the nitrogen. Well, what would happen if it were a secondary amine or a tertiary amine? Well, a secondary amine has two R groups and one hydrogen bonded to the nitrogen. A tertiary amine has three R groups. So let's talk about that first. If you try this reaction with a tertiary amine and all of these are R groups, then when it attacks, whether the oxygen is protonated or not, all these are R groups, this step can't occur. So if all these are R groups and the nitrogen's positive, it's not going to be that stable with a positive charge. There's no proton to remove from it to balance its charge. And so in that situation, we wouldn't be able to do this. What would happen is the oxygen would just swing its electrons back in and kick that out and go back. So the process really can't get anywhere beyond this step if the nitrogen doesn't have a proton to give up to become neutral in charge. So basically with the tertiary amine, there's no reaction occurring here. All right, so let's take a look. What would it look like if I had a secondary amine? In a secondary amine, I'd have two R groups and one hydrogen. So the oxygen could be protonated first. This would attack. That would give you this structure, but there'd be a second R group here. So as long as there's one proton, the mechanism can continue. So something would pick this proton off. Electrons would swing in to balance that nitrogen's charge. We'd have an R group here. The oxygen could pick up a proton, makes a good water-leaving group. We'd have two R groups here. This nitrogen can swing its lone pairs in to push out the lone pair in to push out the water. We'd still have two R groups here. So now we reach a situation where we're able to get this far through the mechanism, but the last step won't work because we don't have a proton on the nitrogen to pick off. So what's going to happen here, the nitrogen still needs to be balanced, but there's no proton directly connected to it to remove, to swing electrons in and balance its charge. So what will happen instead is one of the protons from this carbon or this carbon is going to be removed. It's going to swing electrons in here and push electrons up here. And so that's going to make the double bond here between these two carbons, right here. And the nitrogen is not going to have a single bond because electrons swung up as a lone pair. And so this is an amine, but it's directly in conjugation with an alkene, so it's an amine. And so that's what we form if we start with a secondary amine reacting with a carbonyl. And so that's shown here, right? So here's the key difference. So as we just showed in this mechanism, with a primary or secondary amine, the mechanism is unaffected all the way up until this last step. The difference is in the last step. And so here's what happens. If I start with a primary amine, there were two hydrogens on that nitrogen to begin with. One was already removed earlier in the mechanism. The second one is removed in the last step to produce an imine. If I start with a secondary amine, then the nitrogen only has one proton attached to it. And when that's removed earlier in the mechanism, prior to the last step, I end up with this molecule. So what would happen would be probably another fresh molecule of the secondary amine. That's probably the best base we have around. Would pick off a proton beta to this CN bond. Electrons would swing and push those up, and I would get an enamine as a product of that reaction. And so that's pretty much what the second quiz question was all about, right? So technically that only asked you to show the last step of the mechanism. I really liked how most of your groups showed the full mechanism, so you can at least get practice with that and some feedback on it. If we're looking at the last step of the mechanism though, prior to the last step, the situation I have is the nitrogen has replaced the oxygen. And this nitrogen is part of a six-membered ring. The first proton is lost earlier in the mechanism. So this nitrogen has a positive charge. So then to balance its charge, you got to show a proton being removed from here or from here. And this is equivalent. It doesn't really matter which, because you're going to get the same product either way. If you had a situation where maybe there's an extra methyl group here, that structure is now no longer symmetrical. Would we expect a proton to be picked off from here or from here? Well, it might depend on the sterics, but probably, since this is a pretty weak base, it would probably pick off the proton from here, specifically because that gives a more substituted pi bond. It's more substituted with carbons than on the other side. Right, so either way, the last step would involve the best base in the mixture, picking off a proton, swinging electrons in, and pushing them up to the nitrogen to balance its charge. Oops. And so I'd form an enamine product there. Likewise as well down here. All right, so that forms a basis for a new reaction called the Wolff-Kishner reaction. The first part of the Wolff-Kishner reaction is basically exactly what we just talked about. Taking a carbonyl carbon, adding an amine, except in this case the amines bonded to another nitrogen. Otherwise, the mechanism is basically the same, right? We got a proton, catalyst for the oxygen to pick up first, then the nitrogen can attack. Nitrogen loses a proton, water picks up another proton to make a leaving group. Nitrogen swings electrons and pushes that out. I get this double bond, and then the nitrogen is deprotonated again, and I have this structure here. So this molecule here is called hydrazine. Hydrazine attacks the carbonyl just like the mechanism we just talked about. Once this imine type structure is formed, in a second step, adding KOH and water with some heat will replace that nitrogen with a couple protons. So this is an alternative to a reaction we already talked about. We know that we can convert a carbonyl to a CH2 using zinc mercury amalgam with HCl. The disadvantage there is the mercury is poisonous, and this may react on other sites of the molecule as well. So this is just an alternative. Maybe that reaction doesn't work for whatever reason in our hands. It works well on paper, but not every reaction does. We all know that from lab. So here's an alternative, right? So the mechanism for here is pretty much identical to what we already described. So let's take a look at the mechanism for the second part. So here's what we formed in the first part. We add hydroxide and water and heat, and the hydroxide picks up a proton, forms a negative. So is a negative more stable on an oxygen or on a nitrogen? Normally on oxygen, because it's more electronegative, slightly larger. In this case, though, the negative on the nitrogen can be stabilized with the carbon through some resonance. So even then, though, the resonance is not sharing a negative over a nitrogen and a carbon. It's not going to be as stable as a negative on the hydroxide. So the first step here is probably reactant favored. But once that occurs, there's water, and the oxygen can pick up a proton from the water to reform the OH minus. So we used up an OH minus, we reform an OH minus. So far, we have net zero change on the number of OH minuses. As long as we regenerate the same number we've used up, it could be acting as a catalyst. So once that proton picks up, or once that carbon picks up a proton, we have this structure, and we regenerated more OH minus, so it can pick off another proton and create a negative here. So one advantage here is that the negative is in an sp2 orbital versus sp3, but still the negative is probably more stable on a slightly larger atom with more protons than a smaller one with fewer protons. So again, this step probably is not very product favored. But then the next step, which probably looks crazy to you, is actually product favored. So if this nitrogen swings its electrons in to form a triple bond there, and this carbon here acts as a leaving group and takes this pair of electrons with it, which is very rare, we would almost never see carbon taking electrons away from nitrogen when nitrogen's more electronegative than carbon. But in this case, if the carbon takes the electrons, it forms a negative. So this is very unstable. At the same time, though, this nitrogen forms a triple bond, so we form N2, which is very stable. So the N2 could act as an electrophile, and the carbon could attack it again, and we could go back. But since this is a gas, it starts to bubble out of the reaction and just basically leave. It can't really come back and be attacked by the carbon readily. And since there's water all over, the carbon would just pick up a proton quickly from water and form this product. And that, again, regenerates another OH minus. So we use up an OH minus, regenerate an OH minus. Use up another OH minus by picking up a proton, and regenerate another one in the end. So here, the OH minus is acting as a catalyst since it's regenerated in the same amount that it was used up. And in essence, overall, we started with a carbonyl and we converted that into an alkane. So there's a two-step way of converting a carbonyl into a CH2, another alternative. What drives this reaction forward is the stability of the nitrogen and entropy. So OH minus is relatively unstable, but we're forming that again in the end. So the catalyst does not affect the equilibrium or thermodynamics of the reaction. Right? So we'd have to look at the net overall reaction, and the stability of the products and the entropy of the products really help to drive that process forward. Is the OH minus a catalyst? Yes, it's regenerated in the end. All right, so this slide is just kind of a summary of some of the reactions we've seen so far. Reactions for carbonyl compounds, right? We said for a carbonyl compound, so far we've seen water attack it, we've seen alcohols attack it, we've seen amines attack it, both primary and secondary. We've seen hydrazine attack it. What these nucleophiles all have in common is they're not very strong. They're relatively weak nucleophiles. None of them have a negative charge. So what are some similarities between all the reactions we've seen so far today? Well, one is we want to protonate the carbonyl first. We add an acid catalyst so that it gets protonated. As long as some of the molecules pick up that proton, they become very electrophilic, and any one of these weak nucleophiles that's around can then attack it. Not only that, it avoids a negative formal charge on the oxygen in the immediate intermediate because it's already positive. So we're avoiding an intermediate that has two formal charges by adding the catalyst. The acid also protonates a leaving group, so it's stable and neutral upon leaving, right? So after whatever nucleophile we're dealing with comes in here and pushes this up, this nitrogen would be positive, so it would be deprotonated, and then the water would be protonated, right? Again, don't have the water, or oxygen I should say, pick off this proton. They're too close, or in other words, really they're too far apart because the angles are not going to allow them to get close enough because that would require too much angle strain. So have this lone pair pick up a proton from the acid. Have the nitrogen lose a proton. You wouldn't have the oxygen pick a proton up first, though. They'd both be positive. So the nitrogen would lose a proton, then the oxygen would pick one up, and that helps you with the mechanism. And then generally, the last step usually involves a proton transfer of some kind that produces a neutral product. Another great general rule here is if you are under acidic conditions, if you see in the reaction that there's H plus or H3O plus or some strong acid used as a catalyst, or if you put that acid in there to help the reaction work, you should only have intermediates that are either neutral or positive. You shouldn't form any negatively charged intermediates, right? If there's a proton around, anything that would normally be negative is going to already have picked up a proton. So you can avoid negatively charged intermediates as a good rule of thumb for these reactions. All right, so let's look at the reverse reaction in a little bit more detail. We said we can use water and our acid catalyst to shift these equilibrium back. So before we talked about taking the carbonyl and alcohol and reacting it forward. We said once we form an acetal, we can shift that back by adding excess water because water exists on that side of the equilibrium, would shift it back toward the other side if we had excess of it, right? So again, we're pointing out here how this equilibrium can be controlled and shifted in either direction depending on which of our substances we use as the solvent or in a large excess. So let's just look at the reverse mechanism. So this is for the acetal. It's very similar if you had the imine or if you had the enamine. So any one of these products of addition across a carbonyl compound using a weak nucleophile we've been talking about today can be reversed in the presence of excess water with an acid catalyst. So if I have an acid catalyst and excess water, the water is going to pick up that H plus from the acid catalyst to make H3O plus. That would protonate this, make it a good leaving group. So we don't expect anything to come in and push it out because of the sterics. But this lone pair can readily shift in and push that out to make this. Then again, we're using excess water specifically because it's a reactant. It's got to come in and attack. It would be deprotonated to regenerate the acid. This oxygen would pick up a proton to make it a better leaving group. The oxygen would swing electrons in and push that leaving group out, and then it would be deprotonated in the end. So this reverse mechanism has almost all the same features that we just talked about over here. Right, so if you can become familiar with these key details for next week's exam, it will really help you with the related mechanisms, hopefully. Right, and as we were saying, it's in equilibrium. So we have to use Le Chatelier's principle to control what direction it shifts. Excess water shifts it in the direction shown here. Excess alcohol would shift it back toward the acetal. Similar situation with imines and enamines. If we use excess water, we'll reverse the reactions that were used to form these and convert it back into the carbonyl and amine reactants. You can't use a base very readily, right? We need the acid to start this off by protonating it so that this can swing electrons in and push that out. Too much steric hindrance, too slow for a collision involving OH minus. If we had a base catalyst, that would require the OH minus to like come in here and just push that out. And that's not likely to occur because a neutral OR is not a good leaving group. It's not as stable as OH minus due to solvation reasons. And there's a lot of sterics in that collision. So that step is really not likely. Right? So that's why we need the acid catalyst, not a base catalyst, to protonate that first. That makes it a good leaving group. So now these electrons can swing in and push that out and go through this mechanism right here that we just talked about. You can also do this with sulfur. I think I'm going to skip over this section and not ask you about it on your exam. So you're welcome to kind of skip through this section of the textbook. It's very similar to what we already talked about, slightly different application. There is a reaction where taking a carbonyl and forming a cyclic thioacetal with sulfurs instead of oxygens, followed by hydrogenation using nickel as a catalyst, can do the same conversion we've already seen. Right? So we saw the Clemmensen reduction does this in chapter 19, and we just today talked about the Wolff-Kishner reaction doing this. So we probably don't, in this class at least. It's nice to have lots of alternatives in case the reactions that work on paper don't work in the lab, but we don't need too many alternatives just for the sake of this course. So I won't hold you responsible for that specific reaction or section. And so the rest of this we've already pretty much talked about. We've seen LAH react with the carbonyl. We've seen that mechanism a number of times. We know that the nucleophile is the hydride. Hydrogen's much more electronegative than aluminum. It's going to pull these electrons away and deliver the electrons into that carbonyl. That's going to remain negative. It's much more stable with a negative than either a hydrogen or aluminum until the H plus or product source water, HCl, is added in a second step, and that's going to convert that to an alcohol. And since this produces a chiral center, it's going to be a racemic mixture. So this is a pretty big contrast. I mean, we've already seen this, so I'm not going to spend a ton of time on it, but it's a contrast with what we just saw today. And the main difference is here we're under basic conditions rather than acidic conditions. Right? We're not protonating this first. We can't have any protons around with LAH because LAH can also act as a base. Instead of the hydride attacking the carbonyl, if there were a proton here, it would just pick up the proton. So it'd be pointless to protonate this and then just have the proton react with our LAH. We want the LAH to come in and attack. And since it's a very strong nucleophile with a very large partial negative on a very small atom, it's great at attacking. It doesn't need the acid catalyst to facilitate its attack. the negative on this hydrogen, even though it's a partial negative, is less stable than the negative on the oxygen. So this first step is very product favored. I don't need an acid catalyst to help push it along. The first step here is also irreversible. It's another key difference. Right? When the acid catalyst is present in all the reactions we saw today, each step was reversible, and we can control which way it shifts using Le Chatelier's principle. In this case, though, because the oxygen is way more stable with the negative than the hydrogen, we're not going to reverse this step. You're not ever going to see oxygen swing electrons back in and push out a hydride, right? Don't ever do that. The H- is way too unstable. And we also are, hopefully at this point, pretty familiar with the Grignard. We've seen it work its magic in a number of reactions. The reason this is here is to also provide a little contrast with what we were talking about earlier today, which is to recognize this as a strong nucleophile. And again, it's very reactive toward protic compounds for the same reason the LAHs, and that is the carbon is way more electronegative than magnesium. It's carrying a huge amount of partial negative. It's very unstable. It needs to share that negative badly. And so if we were to react it with a carbonyl compound, it would come in and attack in an irreversible way. I don't need an acid catalyst. If I have any acid or other, even weakly protic compound, this carbon would just pick up a proton instead. So we have to exclude all moisture, all protic sites from being reactive in this case. And so the carbon's going to come in there and attack and push electrons up, just like the LAH creating a negative. And that will stay negative because it's more stable than the negative on the carbon until an acid is added in a second step to simply pronate that oxygen. We've seen this reaction, just pointed out real quick. This carbon is pulling electrons away from the magnesium, so it has a large partial negative. It's going to use those electrons to attack. So in this case, I need three equivalents. This is my nucleophile, this carbon right here. It's going to attack. Where is it going to attack? Well, there's a carbonyl here, there's a carbonyl here. It could attack either one. I don't know which. It's going to push electrons up. Is this effective under acidic conditions? No way. If we have an acid around, then the carbon will just pick up a proton. So we're talking about basic conditions here. We're talking about the carbon attacking the carbonyl, pushing electrons up. It could also attack here, push these electrons up. And so we want to show what's going to happen after that. So if it attacks here, this carbon will then be connected here. So we can show the result of that attack. I want to maybe count these. 1, 2, 3, 4. 1, 2, 3, 4. This carbon here is this carbon here. So also, if the nucleophile attacks here and pushes these electrons up, I'll have something like this. 1, 2, 3, 4. So this oxygen here is stuck. Nothing can happen to it. There's a proton here. There's no leaving group. It's going to have to stay like that until the second step where it gets protonated. But this oxygen is connected to a carbon where there's a leaving group, and it would help entropy-wise to open up the ring, steric-wise to open that up. So it's going to shift these electrons in here and push that out. So this oxygen here is this one here. All I did was rotate this bond and kind of move it away a little bit so it wouldn't be too crowded. But that reforms the CO double bond. So that's when the third equivalent gets involved. So we haven't even added the HCl yet. The third equivalent of the carbon is going to come in here and push these electrons out. So I was going to draw that on the next. I'll draw that on the next slide. So after the third equivalent, this is the substance we would have. So this was the first equivalent we saw attack, this was the second, and this was the third. And then when the HCl is added, each one of these oxygens would pick up a proton and end up becoming an OH. Questions about that? None of these attacks are reversible for the same reason the hydride attack is not reversible. Once this comes in and swings electrons up, the electrons cannot swing back down because there's no leaving group here. A hydrogen or a carbon forming a negative, taking electrons away is never going to happen. It's too unstable. And so that finishes out the addition reactions on carbonyls. Lots of excellent practice there for you to work through. Let me know if you have any questions about these bullet points. Next time, we are going to look at a few more reactions of aldehydes and ketones, including a really cool one called the Wittig reaction. And then we're going to start getting into chapter 21, which is about carboxylic acids. So that's going to be on Wednesday. Make sure you're prepared for that, and you answer the quiz questions for Wednesday as well. So let me know if anyone has any questions right now.